Okay, let's get started. Our second session features two talks on building open source ecosystems. The first talk from Professor Yungang Bao. Yungang is a professor of Institute of Computing Technology, Chinese Academy of Sciences, and the director of the Center of Advanced Computing System of ICT. His research interests including computer architecture and system, and his research has been adopted by industry, including Alibaba, Huawei, Intel, and the research community. He was the youngest plenary keynote speaker at China National Computer Congress, and he was also the winner of CCF Intel Young Faculty Award of the Year, and he also received Outstanding Award of the Youth Innovation Promotion Association Chinese Academy of Sciences in 2017, and won China's National Lofty Honor for Youth Under 40 this year. So today, Yungang will tell us of the 4 steps of building open source chip ecosystem. Yungang, go ahead.
Thank you for the introduction. So today I'm going to talk about the 4 steps to the open source chip ecosystem. So why I come here to talk about this, give this talk, is actually this is because a research project initiated in 70 years ago. Actually, at that time I was still a postdoc at Princeton University, and I came up with the idea to build a new computer architecture. But when I returned back to China, I started to build a prototype. And first I used Spark T1, and after half a year, I gave up since our group gave up since it's inactive, and also it's claimed to be open source. And then, then we made a second attempt to build to try to implement our design on the microbrace on FPGA. It worked. So, and we got funding from NSFC, and we also published a paper on us+. But what next? So how we want to open source our design, and we also want to tape out the design. So, but based on the microbrace, we cannot do that. So then we made a third attempt to implement our idea on RISC-V. I think this gave us opportunities, and then we got funding from MOST, the Ministry of Science and Technology, and we also built the first prototype called labeled RISC-V, and last year we also built the mini FPGA-Cloud to provide services. So I think the first part is our initial idea is to try to build a labeled computer architecture. So it's already open sourced at GitHub. And while we do this research, actually the outcome that I can kind of like a side product is we get many experience in RISC-V and chip Agile development. So today I'm going to talk about the 2 parts. First, I just gave like a short introduction about the labeled computer architecture. So see why RISC-V and the open source chip can help such design. This labeled computer architecture is the key idea here is we can view a computer as a network. So actually, this is such a computer. If we look at this computer and look inside of the computer, actually, this is all packet-based. So like communication through internal packets, like a PCIe packet, network on chip packets, and a QPI packets. So for example, this is a PCIe packet, just like a TCP/IP packet, right? So if we do like a DMA from NIC to the DRAM, the packet goes through to the I/O interface and translate into the system bus packet, and then forward to the DRAM controller. So each controller just like a switch. So based on this idea, we proposed can we build the computer as a software-defined networking? So then, just like the slides, so since from the hardware level, it's just like a network, so then we can add like control level to allow customized policies based on different applications. So this is the basic idea. Actually, we already built we already implemented a prototype, and we found out that this idea can enable research on computer architecture support for like quality of service and security. Since all the packet has labels, and then the control layer can deploy different control policies over these labels. So then we built a prototype. We called it labeled RISC-V. This is it's a SoC. It can scale. It is scalable to multiple FPGAs. And we also built, based on that, we built a mini FPGA-Cloud. So we deploy FPGA as a service, and there are two versions of a cluster of FPGA. This is one cluster of 8 FPGAs. So this is for research, and another is the 32 FPGAs for education. So it's open and free for use. So just contact this email for free use. So here is the tutorial. We gave tutorial last year, and also every code are open source at GitHub. So this is the first part about the research. Actually, without open source platform and open source chip, actually we cannot do that research, just as mentioned before. So the next part I'd like to introduce to share our experience in RISC-V and chip Agile development. So actually, when we talk about open source, so usually we mean open source software ecosystem. So let's look at the open source software ecosystem. So actually, it brings us, it lowers barrier of innovation. Today, it's very easy to develop or to build a smartphone app by just 3 to 5 engineers within 3 to 5 months. It's very easy to build. If you can see in Beijing, it's easy to find such a small group to build an app with just tens of thousands, even tens of thousands RMB. It's very, very, very cheap. So, and with this is because we have the open source software ecosystem. So actually, this ecosystem already provides like 90% of lines of code based on those combination, like a LAMP combination, Linux, Apache, MySQL, and PHP, or Python, or Min combination. They already accounts for like 90% of lines of code. So then the users only need to write about like less than 10% of lines of code to implement their idea. But we just, several speakers already mentioned that for chip development or chip design, there's a high barrier. So usually for like 7 nanometer technology requires more than even more than $100 million and more than 100 man labels. So only very few companies can afford, and also set a high barrier to innovations. So, but we want to talk about open source chip. So, but let's look at this circle. So actually, we found out that there's a deadlock to the open source chip. So these things, basically, this is because the development cost is very large. So nobody is willing to share their design. And then since there's no open source choice, we have to buy. We have to pay high cost to buy IPs. And since we already spent so much money, I want to reduce risks by long time verification. And then it increase the cost over and over. So how to break this deadlock? So our idea, I think, is we need to reduce the development cost. But how to reduce? I think there are already many opportunities. First, actually, is the Bear's law, the golden Bear's law is alive. So actually, it still works. Today we are talking. We start to people pay attention to the IoT chips. So since what is the requirements of IoT chips? Actually, there are many new requirements. So like it should be customizable, and it's small, and it needed faster time to market, low power, low cost. It also needed new programming interface, and one very important factor is low-end manufacturing technology is enough for IoT chips. So the moral story is ending actually brings kind of new opportunities. Since it's ending, then the cost of a mature processing technology is stepping down. So if we look at it like 40 nanometer technology, the cost of 40 nanometer technology, it already stepped down by order of magnitudes. Then it brings innovation, and we can see that if we look at the ISCC papers from 30 years ago, and at that time, so it's as the time goes by, so today the academia papers become accounts for more than half. So why? This is because most academia research based on 65 nanometer technology. The cost of 65 the cost of 65 technology becomes much cheaper than before. So more research groups can afford. That means the Moore's law ending actually sometimes in other perspective actually bring us new opportunities. So then we can see that this is indeed a golden age is coming. So many like the chemical reaction occurs while if we blend like a free ISA open source tools and like new language, emerging applications and clouds, we will see their like chemical reactions. Next, I will show what kind of reaction it can occur. So we envision to build the open source chip ecosystem. I think we have to we have 4 steps to go. The first step is we need to have like open source ISA, open source IPs, and open source SoC, and then we need to have open source like languages and EDA tools, and also we need a low-cost verification and simulation, and also there are system software support like operating systems and compiler. So all of them, we need a platform to support all these 4 paths. So this is if we can build such infrastructure or platform, and then those parts can account for like 90% of lines of codes, then the customers or the users can only need to write like less than 10% code to implement their chip, to build their chip. So next, let's look at how can we achieve the 4 steps. First is about the ISA, IPs, and SoCs. So we already mentioned that RISC-V is actually lays a foundation for the open source chip ecosystem. In China, there are 2 RISC-V allies. This is CRVE and CRVIC. So, and in total, about like 200 members, they already engaged in RISC-V. It's very active in China. And also, we know that, but for IPs and SoCs, there still lacks high performance and high quality open source IPs and SoCs. So should be, we think that what it means high quality, it should be verified by typing out. Now in China, there are 2, we have some startup, they already released the Hummingbird's RISC-V core. This is open source. And we also open source the labeled RISC-V. This is actually is a SOC. And there are also more ongoing open source IPs in China. Just Professor David Patterson mentioned he is leading the RISC library, the lab at Tsinghua and Berkeley Institute, Shenzhen Institute. This library, the RISC library, is which focus on core IPs. And next is about language and EDA tools. So actually now we have more and more high-level abstraction languages that can improve productivities significantly, sometimes by order of magnitude, like Chisel and the Pi MTL. So, and also, actually, there are already a bunch of open source EDA gadgets. So, like, for example, for front end, we have a synthesis open source EDA tool and simulators and verification. The next talk, I think we'll talk about the RISC-V DV. And also for backend, there are also many like open source tools. So, and even for toolchain, there's like Qflow and OpenRoad just in the previous talk. So there are already actually kind of a bunch of like open source EDA tools. What we need to do is just to make it like more stable and high quality and fast. So actually, in our lab, we did some comparison between different languages. So there's a tale of 2 languages. So we try to ask. I asked 2 students, one engineer and one student, to perform the same task and to compare the 2 languages. Here is some interesting result. The first step is to design an L2 cache for the RISC-V rocket chip core. So, one is a 5-year engineer, engineer with 5 years experience, and another is actually a senior student. He is undergraduate. Here is the result. Very interesting. So, for the engineer, he spent 6 weeks and write about like almost actually it's more than 3,000 lines of code, but the effective code is about like 1,700. And for the undergraduate, he spent only 3 days to write 350 lines of code, and then his L2 cache can boot Linux on the multi-core RISC-V and also support the NIC with DMA. So this is quite interesting. So first round, the Chisel is more productive than Verilog by like 14 times and with only 1/5 lines of code. But the engineer refused to accept the truth, the fact. He said, my design, I considered, I have more consideration about my design. My design is better than undergraduate. So the second task is I asked another student this is a junior student. He never knew Chisel. I asked him to translate the Verilog code, the engineer's Verilog code into Chisel, and evaluate on the FPGA board. So here's the result. So actually we can see that direct translation is just one Verilog line, one line of Verilog code is translated into one like Chisel code. So we can see that the performance is already better than Verilog code. And with some advanced features and libraries, actually Chisel design is much better than the Verilog version. So in this, then the engineer, he accepted. So, and we talked about this story to Huawei's engineer. And they said, your engineer only has 5-year experience. You should try our 15 years. So, and actually, I think the engineer is not that weak. Actually, he is going to be the PhD student at Yale University in this floor. So the second, round result is Chisel can achieve better PPA than Verilog. So, and we also performed another task about the open source EDA tool. So here, this time I asked a software programmer, he never knew the EDA and the chip design, to ask him to use the open source EDA tool to generate DDS2 from RTL by open. So here is the result. So this is, we took the RTL code from the GitHub and then used the Qflow to generate the GDS2 with the CMYK 180 nanometer technology. So actually, it works. And but it takes some time. It takes about like several weeks to be familiar with the workflow. And but I still need a stable, and we need a fast and high quality and well-maintained toolchain distribution, just like Debian, Fedora, and Ubuntu for Linux. So there, I think open source EDA tool is promising in the future, but I still need many work to do. How about the verification and simulation? So actually, there are more and more like cloud-based verification and simulation. So because this can lower the barrier of verification and simulation cost by just the pay-as-you-go mode, and rather than buying this very expensive facility from like Cadence or like Synopsys, and we buy like servers with a very high, large capacity memory to run simulations. So like just like Berkeley File Sim and Alibaba's, the Pinto is a company, a chip design company for in Alibaba. So we also have some practice in our university called UCAS, University of Chinese Academy of Sciences. We built an FPGA mini cloud for the labs of undergraduate students for the course, the computer organizing and design. It already served more than like 200 students since 2018. And so the student can only need an account to log into the system, the cloud, and then they can use the cloud to do their labs, to design their own chip. Of course, this is a very small chip, and on the FPGA cloud. And we did a survey, and they found that before the FPGA cloud, every student can get a FPGA board, and then the satisfaction rate is only like 26.8%. But after using the FPGA cloud, the satisfaction rate is jumped to like 87.8%. So this is a huge change. And also there are like about like 64% of students, they turn from unlike system or chip design into like system or chip design. This is actually bring us confidence for the future cloud-based chip design. Finally, is about software tools. So actually, I think we needed to pay attention to 3 layers of software support. And one is chip-oriented, just like Linux or like LLVM compiler. They needed to deal with extended ISA and the sensors or like new hardware accelerators. And the functional level software, it should provide like language support, libraries like JVM or DBMS, MySQL kind of those software. This is just like the Linaro for the ARM community. And I think another important layer is the user and programming oriented, just like Agile provides like APIs for programs or the UIs for users. This is very important for the future open source chip ecosystem. Okay, just like, but today we still have the open source chip ecosystem just like 20 years ago, 25 years ago, in the middle 1990s of this open source software era. So it looks exciting in the future, but now it's still a lot of work to do. We still have a long way to go. In the last year, actually, ICT and the Pension laboratory have launched the Open Chip Lab. We try to build the open source platform to a chip platform for students, for education. We want to make every undergraduate, they can build their own chip, their own open source chip with open source tool, and they can take their chips when they are graduate. This is our goal. And to envision the future, I think probably I borrow my friend's opinion. He said he envisions that in the future there should be like a designless mode. Just like what does designless means? It is design chip without IC expertise. So and then we can make like designing a chip, just like designing a mobile app. Finally, so my conclusion is that now it's time to break the deadlock of open source chip. So and to move forward to the open source chip ecosystem. That's it. Thank you very much. Yeah, currently actually there are already some open source PDKs, just like we use the like CMYK 118 nanometers. Actually, we have also contacting some other foundries in China. Like there are some. So the SMYK 180 is fully open. Those actually some low-end technologies. Yeah, low-end technologies we can access.
Yeah. Yungang again.